Hello, Calculus 2, back to some more parametric equations idea. I wanted to elaborate on some physics. I would be remiss to, I haven't discussed the real important use of parametric equations is in physics when you got two-dimensional motion. You might be trying to talk about the x position of an object as a function of time, and then you might want to talk about the y position of an object as a function of time. So, you know, physics, we love subscripts, so we have this classic equation, the acceleration in the x direction, 1/2 the acceleration in the x direction times t squared plus the initial velocity in the x direction, v naught x times t, plus the initial x position, x is naught, and that's the x position equation. The y position equation has an initial y position, an initial velocity in the y direction, and an acceleration in the y direction. So that's motion in two dimensions. Now, if we talk about projectile motion, where we launch a projectile, then this collapses a little bit. And so let's do that. If we launch a projectile from some initial height, y naught, and we launch it with this initial velocity, v naught, then it takes on this shape, and it comes crashing to the ground. So we're like launching something off a cliff. Maybe we use a cannon or our arm to throw something off a cliff. And when that happens, the only acceleration that's acting on this is gravity, and it's acting in the y direction. So we have so this kind of collapses into this equation. Well, here. So there is no acceleration in the x direction, so that's gone. And the initial velocity in the x direction is this initial velocity. Now I wrote that and I called that v naught. We launched this at a certain angle, and so the x direction of v naught is v naught cos theta. So it's that initial velocity, v naught, multiplied by the cosine of the angle. That's the horizontal component of velocity. And now I'm talking like vectors, but that's okay. So this v naught in the x direction turns out to be v naught cosine theta times t. And then we have an initial x position, but notice where I put this. I've got this starting at this x position of x equals 0, so really I don't have my initial x position is 0, so this is my x equation. It's collapsed to this. My y equation is my acceleration in the y direction is gravity. And we know what gravity is if we deal with feet per second squared. We'll call that negative 32 multiplied by the half. Negative 32 multiplied by the half is negative 16 t squared. The initial velocity in the y direction is v naught sine theta. I didn't write that. That's v naught sine theta there. Times t plus y naught, that initial y height. So there is acceleration in the y direction. It's gravity. There is initial velocity in the y direction. It's different than the x direction. And there is an initial y value. So, all right. I like to do a problem. This is some good stuff. Let's say I started off, the cliff was 80 feet tall. I launched at an angle of 25 degrees, and the initial velocity was 50 feet per second. And my question is, so you could fill in these equations, let's do that, and then I'll ask you a question. So v naught cosine theta t, it would be 50 times the cosine of 25 degrees t. That's just a number times t. I should just fill that in here. 50 cosine of 25 degrees, 45.3, we'll just call that 45.3 t. And y is, here it is, negative 16 t squared plus v naught sine theta. That's That's the 50 sine of 25. Let's just fill that in. What is that? 50 times the sine of 25 degrees. 21.13, I'll just call it 21.1. I am rounding this, t. And that plus that initial y height, which was 80 feet. So there you go. Those are the parametric equations for a launched projectile. Pretty cool. Here's the question I want to ask. I got a couple good questions for you. I'm going to get rid of this information. Sorry. So my question is, how far from the cliff? How far from the cliff does it hit the ground? So this is how you do these physics problems. You know, these are a set of parametric equations. They come together. I've got the x distance as a function of t, the y distance as a function of t. You know, if I eliminated the parameter, this would be the path of the projectile. It would be some upside down parabola there. But I don't want to do that. What I want to do is try to answer this question: how far from the cliff does it hit the ground? And so you end up sort of treating these things separately. I mean, how far from the cliff does it hit the ground means I'm looking for this x distance. I'm looking for x. At the moment it hits the ground. So to determine when it hits the ground, I don't use x, though. To determine when it hits the ground, that's when y is 0. So I need to find the time it takes to hit the ground. So that makes me solve this equation, to find the time it takes to hit the ground. And I'm sorry, but that's a little quadratic formula. I'm not scared. Negative b plus or minus the square root of 21.1 squared minus 4 times a times c all over 2a. You know, we get a couple answers here, but only one of them is valid, the positive answer here. All right, hang on. Let me do this. You can try to check me. I'm going to do 21.1 squared. I'm going to do plus. I'm getting an answer. I'm going to take the square root of that answer. I got another answer. I'm going to add that. No, I'm not. I'm going to subtract. I'm going to do negative 21.1 minus my 74.6. And I'm going to get that answer and divide by negative 32. So my final answer is, wow, 2.99 seconds. I guess I could call that 3. 2.99 seconds. That's when it hits the ground. What was my question? That's the time it takes to hit the ground. I want to know how far from the cliff it is, so I want to know what x is at 2.99 seconds. So the answer is 45.3 times that 2.99 seconds. That's cool. 135.5 if I just round that. So that was fun, 135.5 feet. But I used a combination of these equations, as you could tell. What I did was, what I did when I read this question is, to me this said, find x when y is 0. That's what this said. Find x when y is 0. And I needed the time to help me connect those thoughts. Here's another question while we're at it, since we're having so much fun. I'm going to get rid of this quadratic formula here. Here's another question. What is the maximum height? What is the maximum height? So I like that question. A lot of students will say, how long, oops, I erased it. Remember, how long did it take for this to travel and hit the ground? 2.99 seconds, it hits the ground. Some students will say, oh, it reaches maximum height at half that time. Well, that's a mistake. Hang on. That's true when something's launched at ground level and lands at ground level. Then the maximum height occurs right in the middle. But when it's launched at a height of 80 feet and hits the ground, that maximum height is not the middle of the time. It's not quite the middle. If they're the same, if it's launch height and landing height, then it is. Then it's the exact middle. So what it is, of course, it's a little calculus. It's when the slope of the tangent line is 0. Or it's when the velocity in the y direction is 0. You know, we always have velocity in the x direction. It's moving this way, 45.3 times t, always. But we have some velocity in the y direction, and then it changes to velocity pointing downward after it reaches maximum height. So I'm looking for when the y velocity is 0. Now, in other words, I'm looking for when y prime is 0. What is y prime, or dy dt as we called it in the previous video? Dy dt is negative 32t plus 21.1. I want to know when that is 0. Negative 32t plus 21.1. Set that equal to 0. It's pretty fun. Divide that, please. 21.1 divided by 32. The answer is... Who's my calculator person? I lost my calculator person. Divided by 32 is 0.66 seconds. Wow, that's when it reaches maximum height, because that's when the y velocity was 0. That's when the derivative was 0. What was my question? What is the maximum height? So I need the y position at that time. So I go back to the y position, and I find the y position at that time. Negative 16 times 0.66 squared plus 21.1 times 0.66 plus the original 80 feet. So it won't be too high. It launched at 25 degrees, I guess. Let's see what it is. Negative 16 times 0.66 squared plus the 21.1 times the 0.66 plus the 80. Wow, 86, that's all? Did I do that right? Yeah, I think I did that right. 86.95 feet. 0.96 feet, actually. Cool, that's the maximum height. 25-degree angle, didn't get much height there, I guess. Plus that little 50 feet per second wasn't too much. All right, well, thank you very much. I love these kind of problems. There isn't too many in the book. There was one in the book, and it's asking you to find the angle, which is really a tricky question, I think. There was one in section 10 too. But I might come up with something like this for you. All right, thank you.